An impact crater is an approximately circular depression in the surface of a planet, moon, or other solid body in the solar system or elsewhere, formed by the hypervelocity impact of a smaller body with the surface. In contrast to volcanic craters, which result from explosion or internal collapse, impact craters typically have raised rims and floors that are lower in elevation than the surrounding terrain. Impact craters range from small, simple bowl-shaped depressions to large, complex, multi-ringed impact basins. Meteor crater is perhaps the best-known example of a small impact crater on Earth. Impact craters are the dominant geographic features on many solid solar system objects, including the Moon, Mercury, Callisto, Ganymede, and most small moons and asteroids. On other planets and moons that experience more active surface geological processes, such as Earth, Venus, Mars, Europa, Io, and Titan, visible impact craters are less common because they become eroded, buried, or transformed by tectonics over time. Where such processes have destroyed most of the original crater topography, the terms impact structure, or astrobleme, are more commonly used. In early literature, before the significance of impact cratering was widely recognized, the terms crypto-explosion or cryptovolcanic structure were often used to describe what are now recognized as impact-related features on Earth. The cratering records of very old surfaces, such as Mercury, the Moon, and the southern highlands of Mars, record a period of intense early bombardment in the inner solar system about 3.9 billion years ago. The rate of crater production on Earth has since been considerably lower, but it is appreciable nonetheless. Earth experiences from 1 to 3 impacts large enough to produce a 20-kilometer diameter crater about once every million years on average. This indicates that there should be far more relatively young craters on the planet than have been discovered so far. The cratering rate in the inner solar system fluctuates as a consequence of collisions in the asteroid belt that create a family of fragments that are often sent cascading into the inner solar system. Formed in a collision 160 million years ago, what the fuck is that word? Baptistina? The Baptistina family of asteroids is thought to have caused a large spike in the impact rate, perhaps causing the Chicxulub impact that may have triggered the extinction of the non-avian dinosaurs 66 million years ago. Causing the impact that may have triggered the extinction of the non-avian dinosaurs. Cool. Note that the rate of impact cratering in the outer solar system could be different than from the inner solar system. Although Earth's active surface processes quickly destroy the impact record, about 170 terrestrial impact craters have been identified. These range in diameter from a few tens of meters up to about 300 kilometers, and they range in age from recent times, i.e. the Seacoat Allen craters in Russia, whose creation were witnessed in 1947, cool, to more than 2 billion years. Though most are less than 500 million years old because geological processes tend to obliterate older craters. They are also selectively found in the stable interior regions of continents. Few undersea craters have been discovered because of the difficulty of surveying the sea floor, the rapid rate of change of the ocean bottom, and the subduction of the Earth's floor. The subduction of the ocean floor into Earth's interior by process of plate tectonics. Impact craters are not to be confused with landforms that may appear similar, including calderas, sinkholes, glacial cirques, ring dikes, salt domes, and others. Chicxulub. Pronunciation: Chicxulub. Chicxulub. The Chicxulub crater is an impact crater buried beneath the Yucatan Peninsula in Mexico. Its center is located near the town of Chicxulub, after which the crater is named. The date of the Chicxulub impactor, which created it, coincides precisely with the Cretaceous-Paleogene boundary around 66 million years ago. The crater is more than 180 kilometers, or 110 miles, in diameter, and 12 miles in depth, well into the continental crust of the region, about 10 to 30 kilometers depth. It makes the feature the third of the largest confirmed impact structures on Earth. The impacting bolide that formed the crater was at least 10 kilometers in diameter, 6 miles. The crater was discovered by Antonio Camargo and Glenn Penfield, geophysicists who had been looking for petroleum in the Yucatan during the late 1970s. Penfield was initially unable to obtain evidence that the geological feature was a crater and gave up his search. Later, through contact with Alan Hildebrand in 1990, Penfield obtained samples that suggested it was an impact feature. Evidence for the impact origin of the crater includes shocked quartz, a gravity anomaly, and tektites in the surrounding areas. The Chicxulub Impactor, that means the asteroid that hit Earth, basically. The Chicxulub Impactor had an estimated diameter of 6.2 miles or larger, and delivered an estimated energy equivalent of 100 teratons of TNT. So in other words, boom. Over 1 billion times the energy of the atomic bombings of Hiroshima and Nagasaki. By contrast, the most powerful man-made explosive device ever detonated, the SAR bomb, had a yield of only 50 megatons of TNT, making the Chicxulub impact roughly 2 million times more powerful. Even the most energetic known volcanic eruption, which released an estimated energy equivalent of approximately 240 gigatons of TNT, and created the La Garita caldera, delivered only 0.1% of the energy of the Chicxulub impact. The impact is estimated to have displaced almost 200,000 cubic kilometers of sediment, 2 orders of magnitude more than the amount displaced by the second largest instantaneous deposit, the Nuuanu debris flow in Hawaii. Daedalus is a prominent crater located near the center of the far side of the Moon. The inner wall is terraced, and there is a cluster of central peaks on the relatively flat floor. Because of its location, shielded from radio emissions from the Earth, it has been proposed as the site of a future giant radio telescope, which would be scooped out of the crater itself, much like the Arecibo radio telescope, but on a vastly larger scale. The crater is named after Daedalus of Greek myth. It is pictured in famous photographs taken by the Apollo 11 astronauts. In contemporary sources, it was called Crater 308. This was a temporary IAU designation that preceded the establishment of Farside lunar nomenclature. Nearby craters of note include Icarus to the east and Raka to the south. Less than a crater diameter to the north-northeast is Lipsky. Tycho is a prominent lunar impact crater located in the southern lunar highlands, named after the Danish astronomer Tycho Brahe, 1546 to 1601. To the south is the crater Street, to the east is Pictet. And to the north-northeast is Sassarides. The surface around Tycho is replete with craters of various sizes, many overlapping still older craters. Some of the smaller craters are secondary craters formed from larger chunks of ejecta from Tycho. Tycho is a relatively young crater with an estimated age of 108 million years, based on analysis of samples of the crater raid recovered during the Apollo 16 mission. This age suggests that the impactor may have been a member of the Baptistina family of asteroids. Okay. But as the composition of the impactor is unknown, this is currently conjecture. However, simulation studies give a 70% probability that the crater was created by a fragment from the same breakup that created asteroid 298 Baptistina, which was previously believed to be responsible for the formation of the Chicxulub crater and the extinction of the dinosaurs. However, that possibility was potentially ruled out by the Wide Field Infrared Survey Explorer in 2011. The crater is sharply defined, unlike older craters that have been degraded by subsequent impacts. The interior is a high albedo that is prominent when the sun is overhead, and the crater is surrounded by a distinctive ray system forming long spokes that reach as long as 1,500 kilometers. Sections of these rays can be observed even when Tycho is illuminated only by Earthlight. Due to its prominent rays, Tycho is mapped as part of the Copernican system. The ramparts beyond the rim have a lower albedo than the interior for a distance of over 100 kilometers, and are free of the ray markings that lie beyond. This darker rim may have been formed from minerals excavated during the impact. Its inner wall is slumped and terraced, sloping down to a rough but nearly flat floor, exhibiting small knobby domes. The floor displays signs of past volcanism. Rock on. Most likely from rock melt caused by the impact. Detailed photographs of the floor show that it is covered in a crisscrossing array of cracks and small hills. The central peaks rise 1.6 kilometers above the floor, and a lesser peak stands just to the northeast of the primary massif. Infrared observations of the lunar surface during an eclipse have demonstrated that Tycho cools at a slower rate than other parts of the surface, making the crater a hotspot. This effect is caused by the difference in materials that cover the crater. The rim of this crater was chosen as the target of the Surveyor 7 mission. The robotic spacecraft safely touched down north of the crater in January 1968. The craft performed chemical measurements of the surface, finding a composition different from the Maria. Okay. From this, one of the main components of the highlands was theorized to be anorthosite, an aluminum-rich mineral. The crater was also imaged in great detail by Lunar Orbiter 5. From the 1950s through the 1990s, NASA aerodynamicist Dean Chapman and others surveyed the lunar origin theory of tektites. Chapman used complex orbital computer models and extensive wind tunnel tests to support the theory that the so-called Australian tektites originated from the Rossy ejecta ray of Tycho. Until the Rossy ray is sampled, a lunar origin for these tektites cannot be ruled out. A major geologic process that has affected the moon's surface is impact cratering, with craters formed when asteroids and comets collide with the lunar surface. There are estimated to be roughly 300,000 craters wider than 1 kilometer on the moon's near side alone. Some of these are named for scholars, scientists, artists, and explorers. The lunar geologic timescale is based on the most prominent impact events, including Nectaris, Imbrium, and Orientale, structures characterized by multiple rings of uplifted material, typically hundreds to thousands of kilometers in diameter, and associated with a broad apron of ejecta deposits that form a regional stratigraphic horizon. The lack of an atmosphere, weather, and recent geological processes mean that many of these craters are well preserved. Although only a few multi-ring basins have been definitively dated, they are useful for assigning relative ages. Because impact craters accumulate at a nearly constant rate, counting the number of craters per unit area can be used to estimate the age of the surface. The radiometric ages of impact melted rocks collected during the Apollo missions cluster between 3.8 and 4.1 billion years old. This has been used to propose a late heavy bombardment of impacts.